So, good evening, everyone. Uh, I think it's time to start the session. I am Jitendra Kumar. I am a research scholar from IIT Bombay. So, today we will see some assignments. Can you hear me? Could anyone confirm, please?
Yeah, can hear you.
Thank you. So, today we will see what are the questions in week one, and before that, we will go through some last year problems. So, we will get idea to solve what are the questions asked in assignment one, and we will see some concepts behind that. So I hope that is okay, and I will share my screen as well. Yeah, it will be recorded and it will be available on my YouTube channel. In the end, I will share that link. Okay, so let's start with a problem in which we had to identify in which quadrant our switch will operate. So I hope my screen would be visible. So in this problem, we need to identify in which quadrant this switch will operate on VI plane. So if you have gone through the lectures, so you can see the first switch, which I will annotate here. This first switch is nothing but a MOSFET with a body diode, and one diode is connected in series with that MOSFET. Okay. So generally, the VI plane we indicate like that. This is I, this is B. So we need to find in which direction the current will flow. So let us assume first I will take this kind of polarity, plus to minus from 1 to 2. And if I say the general characteristics of MOSFET, it generally blocks the positive voltage. Sorry, it generally blocks the negative voltage, and the MOSFET, the without body diode, it will conduct from 1 to 2. Uh, it is discussed in the lecture, that is from drain to source, and diode will also continue to flow in that direction. But as soon as we reverse the polarity here from negative to positive, so uh, we can see that current, uh, all the combination of these devices, and that will allow to flow to only diode. This body diode will allow to flow, but this second diode that is connected in opposite to the body diode. So overall, the current direction is not possible. Right? From 2 to 1, current direction is not possible. However, 1 to 2, it is possible. Okay. Anywhere in between, if you feel some ambiguity, you can stop me and we can discuss that again. And yeah, so current can flow from 1 to 2. It means we can mark on this axis that current is flowing uh, in upper quadrant, upper axis, above the x axis, right? We are assuming that this is the positive direction of flow of current and this is the negative direction of flow of current. So negative direction of current will be blocked by this diode 2. Okay. What about the blocking capability of the voltage? So as soon as we apply this negative voltage, let me remove all other ambiguous. Yeah. So this is the negative voltage. This voltage can be blocked by this diode, right? This diode will be able to block as well as this MOSFET. This MOSFET, it will see the voltage polarity across it, like in this manner, and this MOSFET will also block this kind of polarity, right? So if we applied negative polarity, it is easily blocked by two devices out of three devices. So we can say that negative polarity of voltage is blocked. Now we have to see what about positive polarity of voltage. So let me apply the positive polarity of the voltage. So if we apply this kind of polarity, MOSFET will conduct, it doesn't block this polarity, and this diode, it will also see from anode to cathode. So it will also not block this kind of polarity. But this body diode, it will block. Okay. This body diode anode is connected to negative polarity of supply and its cathode is connected to positive polarity of the supply. So it will also block this kind of polarity. So overall, we draw the quadrant in which it will operate. So let me show you what are the options given. I did not show the option earlier, so that first we solve and then we can conclude. So we can see these were the options given in the problem. So now after concluding this graph, we can easily choose the correct option, and you must be able to identify the option as of now. So can anybody tell me which will be the option, which will be the correct option?
Option B.
Option B, correct. Perfect. So it will be option B, and yeah, correct. So option B, I hope it is clear. It is basic question, but we need to go step by step. First, we apply positive polarity, then negative polarity, and then we try to flow positive to negative current and vice versa, right? And then we can judge which kind of polarity it will be blocked and which kind of current it will allow to flow, right? So there must be some problem like that asked in this year assignment also. I think. Okay. No, this kind of problem is not there in week one assignment. I guess week two assignment it must be there. I think no, it is not asked. So anyway, so this was a good problem based on quadrant operation of switches. So I think you should prepare for this kind of problem. So if there is no doubt in this problem, let us move ahead with another problem. Yeah. So one problem is there based on switching losses and conduction losses. So uh, if you have gone through the videos, the professor explained the concept of losses. Generally, four types of losses: switching losses during turn on, during turn off, and conduction losses when the switch is on, and during off losses. However, in many cases, uh, we discard the off state losses because generally in diode also it allows to flow a very small amount of current that is known as ICO or something. So leakage current, which we know if it is an NPN transistor, if it is a NPN transistor, then electron will flow from this side to this side, from anode to cathode. However, some holes will also flow from this P to N because there are two junctions of PN diode. So some reverse leakage current will flow, and due to that, very small amount of current will be there, and that is considered in some cases. I think that is asked either this year or last year. That we will see in continuous session. So let me take a problem based on switching losses. So this is the problem. I hope you are able to see the problem. Let me zoom it out. Yeah. So in this problem, a transition is given. Only on transition is given, and we need to find the peak instantaneous power loss in watts. So basically, it is a special case of this kind of problem. Generally, this kind of problem is framed based on, generally people ask like what will be the total switching losses during turn on, during turn off, and this kind of graph is there. And in diode, sometimes current is rising and voltage is constant. So let me draw possible cases. So this kind of current will be there, and voltage might be like that, and after that voltage will be dropping. So okay, so before going to this problem, we will discuss a very basic question quickly, which will revise our concepts based on what are the characteristics of ideal switches. So this was the problem. It was asked like which one of the following is true for an on state of an ideal switch. So in the very first lecture, professor explained that. Uh, Hello, yeah, anyone trying to speak? Okay, no issue. So yeah, professor tried to explain in his very first lecture that during turned on state, if any switch is there, let's suppose terminal 1 and terminal 2, voltage and current direction we can assume as bidirectional. So any ideal switch is expected to conduct in both the direction, and during that time, uh, Karisma, this question is from last year assignment. We cannot solve this year assignment because you have to solve and submit. We are trying to give idea behind those kind of problems. So we can discuss concepts behind those questions, but we can we cannot totally solve those problems. So this problem is from last year. Okay. So yeah. So what I was saying that for any ideal switch, it is expected to conduct in both the direction, and during that period, voltage across the switch should be ideal, right? So during turn on, voltage across switch is considered to be ideal, and current across switch is expected to flow, or it should have the capability to flow the current of minus infinity to infinity. In practical switches, we have some limitation based on ratings and all that we will see further. And so this is the characteristics of turn on, and during turned off, uh, all the cases will be reversed. Now the switch should have the capability to block the voltage from minus infinity to infinity, and current should be zero. So during turn off condition, ideally no reverse leakage current or no such type of current should flow. However, in practical switches, they exist, but these are the conditions for ideal switches. So I hope you are able to recall those concepts. So now we are moving ahead with the problem. In this problem, we had to find the peak instantaneous power for this given condition. So we will generalize this. We will solve it for any general condition first, and then we will find out what will happen when we find out the peak instantaneous power. Generally, what is the condition behind when peak instantaneous power loss occur in the switch? Okay. Okay. So the transition of switches are like that. Since it is getting turned on, so during turn on, voltage will try to get reduced to zero, and current will try to rise till its rated current. Okay. However, there will be some limited voltage in practical switches. Generally, in transistors, we assume VC sat as of zero point 0.2 volt, right? So there will be zero point 0.2 volt in practical switch, but here it will be zero. Here we will consider it zero. So this is the voltage waveform, and this is the current waveform, and the duration is given T on. So we know energy. We can derive power from energy, and that is nothing but V I dt. Okay, and how much energy is lost during turn on period? We can integrate it from 0 to T on, and when we try to find the power, that will be energy by time, right? So basically, E into switching frequency of the switch. So we will start from deriving the energy expression here. So for that, we need the expression for both voltages and currents. So voltage we can write as, since voltage is the drooping slope, so we can write it as V naught into 1 minus T by T on. Okay, and V naught, I guess it is given here. V naught is given 100 volt and I naught is given 10 ampere. So we will plug in those values. So V naught is 10, and we will try to write the expression of current also. Current will be I naught into T upon T naught. And then we have to club both voltage and current expression, and we have to integrate. So we will do like that. T naught I naught into T by T on to 1 minus T by T on dt. Right? This will be for the period from 0 to T on. Right? We are assuming that this instant as 0 and this instant at T on. Let me show you the complete graph. So this period is given T on, so we will assume that it is getting started from 0 and it is getting turned on at T on. So the transition period of switching for turn on, its period is T on. And this is the general approach we solve any kind of switching losses problem based on that. So V naught I naught are constant anyway. So V naught is 100 and I naught is 10, so 1000. We will take it outside and we will multiply it T minus T on T square minus T on square dt. I hope it is fine till now. So further simplification we can do that. Now we can integrate directly. T on is given. T on is anyway constant. So T dt will be T square by 2 T on minus T square dt will be TQ by 3 T on square. Okay. And we have to plug the limits of integration from 0 to T on. Now we will plug in T on in all T's. So that will be T on square divided by 2 T on minus T on cube divided by 3 T on square. Okay. Yeah. So after further simplification, you will get T on by 2 minus T on by 3. Any doubt till this point?
How you got voltage and current expression?
Okay. That was given in the problem, this graph. If you can see this clearly, are you able to see the graph?
Yes.
Yeah. So if you try to write down the expression of current,
Uh,
what will be the expression? This current expression will be this 10 into T by T on. How I am writing this? This total period is T on and this is on T axis, right? So if you try to write it as y minus y naught divided by x minus x naught is equal
okay.
to y2 minus y. You got it?
Okay. Okay, sir.
Yeah, thanks. So, yeah, any other doubt? Okay, so I think I should go on. Yeah, this session is being recorded. I am not doing the recording through Google Meet, but it is recorded and I will share the link of the recording. Okay, so after further simplifying, you will get 1000 into T on by. So this is your energy lost during on transition. Okay, so we have concluded energy. Yeah, any doubt, Santi? You want to say anything?
No, 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 no.
Okay. So, similarly, if this kind of graph would have been given for off transition, in off transition, what will happen? They will do the same, just they will interchange these terms. Now, for off period, what happens? Voltage will rise and current will flow till all the way to zero, right? So, voltage will rise till its rated value, and current will go to zero. So this will be the current waveform and this will be voltage waveform. Did last discussion. Actually, this is the first discussion session, so there was no any last session. So,
Uh, Hello, Jitendra. Actually, for this is third session, no? First I attended, but I missed the second one. Now I'm attending the third one.
okay. Generally, there are three live sessions per week, and in all those three sessions, three different member discusses. So, those
Okay.
last two sessions were conducted by other two members. So, anyway, you can search it from YouTube, or I will try to send if you mention your email ID in chat box. So, I will try to send the link. Okay.
Okay, thank you.
Yeah. So, I was discussing that. Uh, For turn-off transition, voltage will rise from its zero value to the rated value, and current will drop down from its rated value to zero value. So transition will be same. The slopes are interchanged for voltage and current, and you again can write the expressions easily based on the slope equations of voltage and current, and you again do the same operation on both voltage and current, and you again will be able to calculate the energy lost during off transition in similar way. And when you find total energy during on and off, then you can easily find the power loss will be this is switching power loss, that will be summation of switching power loss during on and switching power loss during off transition. And we have computed energy lost during on transition, and if we wish to find the power lost during on condition, we just need to multiply energy lost during on into frequency, right? Power is nothing but energy by time, and time is total time period, and inverse of time period is frequency. So we were given with frequency in the problem. Let me go back. So in the problem, you can see it is mentioned that total switching time period to be 50 microsecond, and this turn on transition is happen in 5 microsecond. So we have total switching time period that is 50 microsecond. So T we can write as 50 microsecond, and T on is 5 microsecond, and the data are enough to compute power loss during on period. So we will do it. So till now we have lost energy in terms of T on, and T on we will plug here as 5 microsecond, and total time period as 50 microseconds. So we can also write it as T on by T. So, and that is nothing but 1000 by 6 loss during on, that is 1000 by 6 into T on by T. I did nothing. I just wrote the expression of energy lost during on transition and divided it by time period. And if I further simplify it, 1000 by 6 into T on 5 microsecond divided by total T, that is 50 microsecond. So it will be 100 by 6 watts. So it is the answer for the problem. Sorry, for if it has been asked for only lost power during turn on transition. But question is asking something else. So I explained these concepts just because of these kind of problems are very general and it can be seen anywhere. And I guess sometimes back it was asked also in. So you can see this kind of problem. So basically, the problem was particularly about we need to compute peak instantaneous power. Okay. So if we know this basic approach or this approach, then we can easily find out what will be the peak instantaneous power. So this is total power lost during turn-on transition. Yeah, I will send the link for recorded video. Don't worry. Yeah. So this was the expression. After this point, we try to plug in all those values in the expression. Okay. So in this expression, we know if we have any expression in terms of any variables and we try to find any maxima or minima value, we need to differentiate that expression, right? So we will do the same here and we will take it like 1000 was nothing but the constant multiplication of v and I, the rated value of v and I. So if we can write this expression again, vi t square by 2t on minus t cube by 3t on square. Okay. This was the expression here, and if we differentiate it, we will get same thing. Also, if you try to apply intuition for this kind of expression, so let me go with a very basic approach with intuition kind of approach. If this is the expression 1 minus t by t on, this is not complicated problem. Uh, what is your name? Sorry. Hayumanuan, this is not a complicated problem. If you have any complication in this problem, you can stop me in between and I will explain that again. Just I am trying to solve it with different ways so that you get the approach. Basically, this problem was asked like you need to find just peak instantaneous power. But what I did instead to provide you more insight of this kind of problem because this kind of problem can be framed in many ways. So if you know the approach to solve from zero to whatever the level it can go, then you can find out any intermediate parameters or any intermediate values. So that's why I am doing this. Okay. So okay, I will summarize this problem once more. Just let me finish this expression once. So this was the expression of v and I was I into t by t on. So this is V into I, that is power. This is power expression. We need to find peak instantaneous power. That will be nothing but just in simplified format T by T on minus T square by T on square. Okay. If you need to find when the peak or when the maxima will occur, you need to differentiate it once dp by dt and you have to equate it to 0. And anyway vi is constant, so you need to differentiate t by t on minus t square by t on square. Okay, if you equate it to 0, this differentiation, then you will get the point at which instant the maxima will occur. So if you differentiate, that will be 1 by t on and Tion also we can take outside. So let us differentiate in terms of Tion, because Tion is also another thing, T by Tion. Okay, this is just in format of d minus d square is equal to 0. So if you do that, or x minus x square, so if you differentiate first term, it will become 1, and the second term will become 2 into t by t on, and you equate it to 0. So what you will get, t by t on is equal to half. It means the time instant when maximum power loss will occur, sorry, the peak instantaneous power loss will occur, that is nothing but the t on by 2. And the t on by 2 instant is this point, the intersection point, right? From graph also you can visualize the maximum of two products will occur when they are intersecting. So that's what I just verified from the expression. Otherwise, you can also go with general approach of power expression, and you can plug in those values. But the better approach would be just write the expression of both voltages and current, and you differentiate it once with respect to the variable, and you will get the exact point. Okay, so we got the instant where peak instantaneous power loss will occur. That is nothing but t on by half, and if we plug in those t on by half in the expression of power, that is, this was the initial expression of power, and if we plug in here t by t on is equal to half, so we will get p is equal to v 1 minus t by t on, which is half, and I into t by t on, that is again half. So you will get half into half, 1 by 4 v into I, and v value we know 100, and I 10 divided by 4, so that will be 1000 by 4, 250 watts. So any doubt in this problem? I will explain it again. Okay, do not worry. So I will explain it one more time, what I did, why I did, and where did we conclude. So this problem was framed based on power loss. So power loss, there are four kind of power loss we explained: turn on, turn off, switching losses, turn on conduction losses, and off losses when switches are off. Okay. So generally switching losses are typical. They are, different characteristics of voltages and currents you will be able to see. So for turn on, obviously current will rise and voltage will fall, and for turn off, current will fall and voltage will rise. So, and this kind of waveform you will see in those problems. So the first thing you need to do, you need to find the expression of voltage and current. Okay. So that what I did, I wrote the expression of voltage, that was V naught into 1 minus T by T on, from the formula of slope. If you apply y is equal to mx, so the with formula of slope you will get the expression of voltage as V naught into 1 minus T by T on, and you will get the expression of current, that is I naught into T by T on. We can integrate and we will obtain the energy lost during those periods. Okay, so that's what I did here. We computed energy lost for that period, and we know energy is we know the relationship between energy and power. If you multiply frequency, switching frequency, or you divide with time period to energy, you will get the power. So I did integration, so I obtained energy loss during on transition, and then I divided it with switching time period. And here with division, we got power loss. Okay, so we got power loss for on transition of switching. But this was not the problem. This was just to explain the concept. The problem was to find out the peak instantaneous power loss. Okay, this is the problem here. I will show it one more time. We need to find peak instantaneous power loss in watts. So if we know the expression of voltage and current, and we just need to find out the instant where this maxima will occur at that time instant, if we plug in that time instant in the expression, we will be able to obtain the power loss or peak power loss. So for that purpose, what I did, I just differentiated to obtain that point, that maxima point. I differentiated it and I equated that to zero. This is the expression here. This is the expression here. I differentiated with respect to t by t on, since those were the variables. So after differentiation, I got t by t on is equal to half. Okay, what you do generally in mathematics, you put those values in power expression and you get the answer. You and hence after putting that t by t on is equal to half in this expression, I obtained this answer, that is 250 watt. So 250 watt was the answer for this problem. Is there any still doubts in this problem? Okay, so I will consider it no doubt in this problem anymore. Thayu Manwan, you had doubts, so I hope it is clear to you. Yes.
We got basically clarity up to 100 by 6 wattage. Then the next step to achieve 250.
250. Yeah. Okay. See, 100 by 6, what was total power loss during on period? Okay.
Perfect, perfect.
Yeah. But its peak instantaneous power will be something else that will obviously larger than this value, right? Did you get that point? Why peak
Perfect, perfect.
instantaneous?
Yes,
Yeah.
yes, yes.
Yeah. So to find out that peak instantaneous power, I restricted myself at this step and I differentiated this expression with respect to t by t on, and I got that point t by t on is equal to half. And then I plugged in that value of t by t on is equal to half in this expression, and I got peak instantaneous power.
Okay, understood now. Understood.
Yeah, thanks. Okay, so I hope this problem is clear. I will move ahead with another problem. So, take So this is based on diode. Uh, in diode, we need to compute certain losses, and with respect to its characteristics, its graph is given and its circuit is given. I will state the problem. So this is the typical diode characteristics you must have seen from lectures also. And this is a circuit given. Okay. So the problem is said that we need to compute maximum power transfer from source to load. So this problem will test the concept of maximum power transfer theorem along with the concept of your diode characteristics and diode modeling. How do you model a diode? So that we will see step by step. Okay. So this problem, it is given that RL is 3 ohm. Let me zoom. RL is 3 ohm given. Sorry, no. RS is 3 ohm given. This is 3 ohm given. We need to find out the value of RL such that this circuit will be able to transfer maximum power from source side to load side. Okay. So since it is a diode, we can model a diode with a forward blocking voltage, that is VF, and dynamic resistance, that is RD. We can replace this diode with this circuit. I hope you agree. Now, for maximum power transfer, there is one condition. Actually, there are certain three conditions when impedances are included. But since it is a diode, there will be only one condition that will deal with resistances only, and that says that maximum power will be transferred from source side to load side if let me draw a Thevenin equivalent circuit. So this is your load resistance and this is your Thevenin resistance. So Thevenin resistance generally combines all the resistances in the circuit equivalent kind of resistance. And if you derive, generally there are some differentiation operations are applied in general circuits, and based on that, a condition is concluded that when RL is equal to RTH, then your maximum power will be transferred from source side to load side. Okay. So if we need to find out the value of RL to obtain the condition for maximum power transfer, we need to find out the total resistances, right? And total resistances, I mean RS is given. We just need to find out the dynamic resistance of the diode. And do anyone has idea how to obtain dynamic resistance from this problem? I guess you must have idea because in lectures it has been discussed that with the help of graph or with the help of dynamic characteristics, how do you model a diode? And this is generally, yeah, slope. So many people are answering. So slope of this curve. So this diode is modeled as VF plus RD. Okay. So VF is nothing but this cut-in voltage. Yeah, V is equal to IR. V is equal to IR. That will be definitely. the thing here. So let me go with a step-by-step approach. So diode is modeled with VF plus RD, and VF is nothing but this cut-in voltage, that is zero point 0.5 volt here. Okay. And RD we can compute from the slope, as you told us. That slope will be, let me compute the slope. So RD will be del V by del I, and del V from this zero point 0.5 volt to zero point 0.8 volt is 0.3 volt, and del I is zero point 0.9 ampere to 0 ampere. So zero point 0.9 ampere. So RD will be 1 by 3. Right? RD will be 1 by 3 ohm. So your dynamic resistance is 1 by 3 ohm. That is nothing but 0.33 ohm. So your diode is modeled. Now you can replace this circuit. I will replace this circuit again. That source voltage was 10 volt, I guess. Yeah, 10 volt. And the diode is modeled as VF was zero point 0.5 volt, and RD is 0.33 ohm, and your RL is given. Sorry, one more resistance was given, source resistance. Source resistance was 3 ohm. And RL we need to find out. Perfect. So till this point, I hope there is no doubt. If you have, please open the discussion. This is overall we have discussed till now. So after that, we are going to find out RL for maximum power transfer. So RL is equal to RTH. I told that this will be the condition. So how to find RTH? How to find RTH in this circuit? Anyone? Could you please help me in deriving the value of RL, or sorry, RTH? Yeah, Anaga, you directly told the answer. Okay, so
Take voltage source equal to 0 and find look back from the RL point.
great. So that is the approach we will apply. So we will sort the voltages. So we are indirectly applying zero voltages. So uh, I will draw the equivalent circuit. We will make voltage sources as zero, and we are seeing from this point RTH is 0.33 ohm and 3 ohm. So both resistors are connected in series, so we can directly add it. That will be 3.33 ohm. So we got RTH, and indirectly we got RL, which was asked in this problem. Okay. So this is how we proceed to compute maximum power transfer in such kind of problem, or any kind of problem. How the key point is to how to model a diode in the circuit. After that, there might be some other concepts which can be tested, but the basic ones, how to model a diode based on its VI characteristics. Okay, so all the information was given in this VI characteristics, right? VF was 0.5 volt, and RD we computed from del V by del I. So this is the answer of this problem. RL will be 333. Still, if anyone have any doubt, can open the discussion or can move ahead with some other concept. So in this same problem, uh, other things can also be tested, like how much power is being transferred from source to load. Since we found out the value of RTH, the another problem is the maximum power transfer from source to load. So let me write the problem. From source to load. So for that purpose, we need to identify the current, right? And if we know the value of current from the circuit, and we will multiply it with RTH, and you will get, or RL for that matter, you will get the value of maximum power transfer. Okay, so this is the circuit here in front of us. We just need to find out the current, and I square RL will give us the maximum power that will be transferred from source to load. So quickly we will compute the value of current. So that current will be 10 minus 0.5 divided by 3.3. I think 3.33 into 2 times, right? RL plus RTH. So that will lead to the value will come out to be 1.425 ampere. So this is the value of current that will flow from this circuit. And if we get the value of current, we will compute the power I square RL. So maximum power will be I square RL, that is 1.425 square into 3.33 ohm, and that will lead to 6.76 watt. Okay, so it is the maximum power that will be transferred from source to load. Okay, so here the forward voltage is must to consider in the circuit. Otherwise, if you forget to include the forward voltage, you will get some another value and that would be wrong. So that was the concept behind it. Now another very important concept, what will be conduction loss? So if anyone remember the expression of conduction loss that professor taught in the lecture, so that we will recall from this problem, right? So question 3, from the same circuit, we need to find out the conduction loss. Just excuse me for a second. Yeah, so we are here to find out the conduction loss, and I would like to recall the concept what professor explained for conduction losses in diode. Anyone is able to recall that expression of conduction loss? Okay, so During conduction time, let me draw the graph. So during conduction time, voltage will be almost negligible, or that forward voltage, right? Plus the drop across that diode, uh, so dynamic resistance. So during a conducting period of the diode, it was modeled as forward voltage plus IRD drop. Since it is conducting, the current will flow through the switch, and it has a dynamic resistance. So that will be some voltage, right? Some finite voltage. So let me denote with different color. So this will be your VAK from anode to cathode, which will be minimum, and VAK is nothing but VF plus IRD, right? And IAK, right? What will be the current will flow across that device in the color again. So this will be current IAK. So this is the waveform of voltage and current during turn on, right? So if we need to find the conduction losses, we need to express in terms of some expression, right? Then only we will be able to find out the loss. For that, I am going to write the expression for conduction loss. So that is nothing but, again, any power expression will have this kind of thing for the conduction VAK, IAK, dt. So this is the thing here. Now VAK we have expressed in terms of VF and IAK into RD. So we will plug in those values 0 to T VF plus IAK into RD into IAK into dt. Okay. Now try to relate it with the lecture thing also in parallel. If you write it, or if you segregate both the terms, VF into IAK plus IAK square RD to dt, it is audible for me. Okay, someone has raised hand. Yeah, Anaga, you want to ask something? No audio. Hello.
Okay, sir. Is it clear? That's
Okay,
clear.
thanks a lot. So I guess I am audible now. You, whoever is not able to hear me, just log off and rejoin. Okay. So uh, this was the thing. I went up till this point. VF into IAK plus IAK square into RD into dt. So we segregated in two terms, conduction losses, right? And now I will further segregate it, and you will be able to see two different type of expression here. That is VF into IAK dt. IAK is constant, VF is constant. So I will ask which type of loss is this? Here IAK square into RD dt. So as professor also explained that this is nothing but RMS loss across the resistance. Okay, IAK square RD due to dynamic characteristics of the diode, and this is the average power loss during conduction period, that is VF is constant. You remember we modeling diode with one element was VF and IAK was flowing. So it will give us the average power since VF is constant. So if you have VF and IAK curve also, you can compute the area of that curve and you will directly get the power loss during that period. And another thing was dynamic resistance, that was RD, and again IAK was flowing through that. So if current is flowing through a resistor, so power will be IRMS square. So that's what we derived it here, and we got this is the RMS IRMS square R, and this is VI. So these two different terms are there, and that is easily visible from the expression, right? Now, if we know the expression, if we know the basic behind the switch, we will be easily able to compute the conduction losses. So we will go ahead and we will plug in all those values. The conduction is equal to Vf If Iak into dt. So that will be Vf was zero point 0.5 volt and Iak was we computed for this 1.425 ampere. Okay, was 1.425 ampere, right? 0.5 volt, 1.425 ampere, and again for constant signal, it, it will not be any difference for RMS and average. If any signal is flowing like constant, RMS and average value will be same, right? So IRMS square, this is VI, this is IRMS square R. So if you put IRMS is equal to 1.425 and R is nothing but RD, and RD was 0.33 ohm. So we are clear with all the value. We just need to multiply with each other. So 0.5 into 1.425 plus IRMS square 1.425 square into 0.33 ohm. And if you solve it further, you will get 1.388 watt. Any doubt in this solution from starting to any point? And one very important point, uh, why generally we care about switching loss in switches in power electronic devices. When we were deriving the power loss during on transition only for switching loss, it was 250 watt. Okay, just for switching, it was 250 watt. And I hope you will be able to appreciate the point that conduction losses is so low, that is 1.388 watt compared to 250 watt. So you can feel the difference between conduction loss and switching loss for the same circuit. And if you add switching off transition, you will get total 500 watt and 500 watt respected to 1.388 watt is very high. That's one point. So again, any point, any doubt in this solution? So after all this derivation, you can just write in one formula that will be the conduction loss for any diode, that will be forward voltage drop into average current plus RMS current square into RD. If you are asked any MCQ kind of problem or just numerical answer type where you have to plug in the value of loss, there you can easily apply this formula VF into I average plus IRMS square into RD. Since diode has two components, one voltage source or voltage drop is modeled as a voltage source of forward voltage drop, and one is dynamic resistance. So you just need to compute those two values. Why switching loss high? See, another in any power electronics devices, why we use any power electronics devices? So in further session or in further lectures also, you will see that power electronics devices are generally used to switch at very high frequency. Okay, generally you won't see any normal diode like any low rating of diode or any transistors to get switched at turn on turn off at so high speed, and we are doing it purposefully. We are doing it intentionally to get our desirable outcome, right? uh, just I am taking an example of inverter. We do a very high switching in inverter in one time period only, just to get our desirable sinusoidal kind of voltage. That switch is not there to give us the sinusoidal voltage, right? It gives some harmonics also in the process, but it is not there to give us that desirable outcome. But we we exploit that switch to get our desirable outcome. To get that desirable outcome, we switch it so many times, and for any switch, if you operate at like if you are doing switching, you are doing turning on, turning off so many times, its frequency will be higher, and power loss is directly proportional to frequency. Okay, so if power loss is directly proportional to frequency and you are doing switching so at so high frequency, your losses will be higher. I hope this will be justifiable. Uh, Please do not worry about recorded session. I will say that. I average equal to IRMS. Q. So why I average equal to IRMS? See, current is flowing through, since that was a DC circuit, right? Let me bring back that circuit again. See, this circuit. This circuit is a DC circuit. Here continuous current is flowing in DC manner. So if you try to derive from expression also, you will get the same thing, right? For any constant signal, this kind of signal is there, current. Whether you find average of current or RMS of this current, you will get same thing. But things will change when the nature of current will get deviated from this kind of waveform. That's why for sinusoidal, for triangular, the RMS and average are different. But here, for this particular, this specific case, the RMS and average are becoming same. So that's why I wrote RMS and average equal. Is it fine, Akash? Or Anaga, are you satisfied with the answer? Why switching loss is high? Great, thank you. So, Sat Altaf is asking week 2, question 9, how to find total power loss. That I will see what is there in 9. Okay, so dynamic characteristics of the circuit given. See, Sat, you are asking about this problem.
Uh,
Okay, so here all the transitions are given, right?
yes, sir.
I just discussed this kind of transition of switching losses. Right? So I hope let me put positive square is duty. Yeah, but we are Akash, we are considering the conduction time period as one time period. So out of similar to what we considered as switching time period as a one time period. In that manner, we considered one conduction time period is one time period. So that's why we were able to take d is equal to 1 in that particular case. There is the waveform. Yeah. So just to tell you, for conduction, just for the sake of conduction, we are taking it as a one time period. For how much duration it is conducting, we are taking it as a one time period. For the reference, I would like to ask you, you go to lecture number. If you want to understand this switching loss concept, I guess that is explained in lecture number 5, where conduction loss. The title of that lecture is Conduction Loss by Professor Umanand. In that NPTEL lecture, you go there and you just see it once more. You will get more clarity. Okay.
Okay, sir. Thank you, sir.
Yeah. So where was I? I was asked about that problem. So this is the problem. Here, I hope you will not find any trouble in computing uh, turn on transition and turn off. This is turn on transition. This is turn off transition switching loss. Since I discussed these two concepts, okay. The remaining thing is this conduction loss. This is conduction loss. Here you just need to multiply VC into IC, right? And one during turn off, and that turn off condition is, if I am not mistaken, some reverse current is given in the problem. ICO is given, right? You can see that ICEO, and you utilize that ICEO and you multiply it with VC, you will get turn off losses during when switch is off. When switch is off, some current is flowing from this side to that. So this switch voltage and this current will contribute to this loss. And this conduction loss I just explained. Turn on switching and turn off switching loss I explained in the earlier. So I hope you won't find any trouble. Raja. So Altaf, I hope this is okay. I cannot solve this problem since this is a assignment problem.
Okay, sir.
Right? Okay. So Dharmesh, yeah, definitely I will share the link. Okay, right away I will share my of that channel where this lecture will be uploaded within half an hour.
Basically, even if we have the turn-off loss very less, still we can consider as we have the values given in the problem, right?
Yes, yes, you have to consider that. That's why this problem is given. You can compare all those value of losses by on your own.
Yeah.
That's why intentionally ICEO was given. Problem.
Yeah.
So I am sharing the link of the YouTube channel where I will upload. You just go there and in chat box you can see that link. Okay, so any doubt regarding this problem or earlier problem, this conduction loss problem again? Otherwise, we will move ahead with some another problem. Switching loss same as T on and T off loss. It can be same. Generally, the slope is same for both turn on transition and turn off transition, but it might differ also. So you have to verify on your own. You know the slope of both voltage and current. You just verify it once on your own. Okay. Generally, the problem they keep it same, but for twist they can change it. So it is always better to verify it on your own. Generally, switching losses. Yeah, you are correct, Anaga. Switching loss is higher than conduction loss in SMPS since SMPS is also a switching kind of circuit, right? Where switching devices are employed to get our desirable outcome. So wherever this kind of things we employ, switching losses will be always higher. How can find other data from data C? 10th question on that. Yeah, that I knew that that question will come up, Dharmesh. Just let me. You are asking about 10th question of data. So first you go through the data sheet of the diode. I hope that is Schottky diode in the problem. Let me see. Oh no, it is an ultra fast diode. So you open that diode data sheet. I think I have that data sheet with me. So this is the data sheet. That this data sheet you will be able to download it from resource file from that NPTEL module, and you see you observe all those data and to see this kind of waveform, right? This is the waveform where everything whatever is asked you can extract the information you can extract from this waveform. TA is given, TV is given. If you read it once, you skim through the data set once. I think it is not more than 4 or 5 pages. You skim it through once, you will get the answer. You just need to find out the uh, what is the question? Reverse recovery current, peak current, if I am not wrong. Yeah, peak reverse current during turn off. So you are given with slope in data set. You may find reverse recovery time, and that's all. Dharmesh, is it okay? Okay, I hope that was quite a good hint. Di by dt, you can write it in term of IRM by TA. Okay, Di by dt you are given. TA you may find from the data. Okay, and that's all. You will be able to compute IRM. Yeah, Kaushik.
Can you elaborate little bit about BCE SAT?
BCE set. Okay, I think I must have some problem based on that. So I have a problem based on a VC set concept kind of thing. I will discuss that problem, and I hope from that problem you will be able to gain the concept of that. So I will take a problem based on BJT. Okay. So this is the problem. Here we need to identify in which mode it is operating. Linear, linear saturation, cutoff, okay, or reverse active. So this is the problem. And excuse me just for 1 minute. Okay, so I'm back. So I hope you have read the problem. Okay, so VC SAT is considered the drop of voltage. I hope you are able to see the problem and hear my voice.
Yes.
Yeah, thanks. So VC SAT is generally given when switch is work when the transistor is working as a switch and the voltage drop across the switch would be equal to VC SAT. And if you operate in linear region, you will see the voltage drop across switch will be much higher than VC SAT. And this VC SAT value is why important. If you see from transistor characteristics, let me draw that characteristic as well. So this why the concept taught by the professor. You can see from this waveforms that VC SAT when the switch is conducting, when switch is on and it is conducting, then the drop across the device is generally VC SAT and it is very low. When transistor is considered as ideal, it will have a voltage drop of zero, right? But obviously it won't be ideal. It is a practical transistor. So the drop across the switch in saturation region, that is VC SAT. And if it goes in active region, just uh, let me take this one also. When it goes in active region, yeah, so these are the active regions. And before this point, it was in saturation region. Saturation region is the region where IC is less than beta IB. And let us suppose if our transistor is operating as a switch in linear region, what will happen? Although it will not happen, but let us suppose we have a VC. So let us suppose VCC is 10 volt and R is 1 ohm, and we have given some base current that is something, and the collector current that will flow, that will be beta times of IB. Okay, so let us assume IC is 5 ampere here and IB is beta is 50 or 100, so 0.05 ampere is IB. Okay, we arrange such that beta of this transistor is 100 and IB 0.05 ampere. So I see beta IB, that is 5 ampere, and its RC is 1 ohm. Generally, it will be milliohm. Just for the simplification sake, I am taking 1 ohm. So if this kind of thing is there, we give we give the control signal, that is IB, really small, 0.05 ampere, and it will lead to a high current in collector since it will be multiplied with beta, and it will lead to a current, collector current of 5 ampere. Now see what will be the voltage across our transistor VCE. How much it will be? Just basic KVL, 10 minus 5 into 1, That will be 5 volt. Now, if 5 volt drop is there across that VCE, and we have devices, we operate our power electronics devices for higher rating. So you can observe that conduction losses will be so higher. Let's say if even the IC is 100 ampere or the device is rated for 100 ampere, your conduction losses will be 500 amp, 500 watt. So conduction losses will be very high if you operate in this manner. That's why during conduction period, we operate it in saturation mode, and in saturation mode, IC will not be equal to beta IB, but IC will be much less than beta IB. So you can increase your IB, of course, but your IC will not increase, and hence that manner it will be called that it is operating in saturation region, and your IC will be very low. Let us assume zero point 0.5 volt or something. So that will lead to a very small drop, and that will operate uh, like VC sat, we assume for that process, and VC sat will be zero point 0.2 volt. And if zero point 0.2 volt will be there instead of 5 volt, of course, no matter, definitely the losses will be very low, comparatively very low when it is operating in this fashion. So this concept was explained by professor also, I guess.
Hello,
Yeah.
can I ask question?
Yeah, please go ahead.
If the earlier question, it is related to previous question, the P
Mhm.
conduction loss of any switching wave shape, VC is set into I into D. Here in D we have to consider turn off, turn turn on, turn off as well. Is it considered or we have to consider it separately?
If in the problem every period is given, then D you must need to consider as turn on period divided by total time period.
Okay, but show me that picture. I will previous picture where
Oh,
this equation is there. He in this equation,
yeah.
this conduction loss. Okay,
Yes.
conduction loss. Uh, here is 5 ampere current. It is when it is conducted, it is drawing 5 ampere current. At that time, we see that is 0.2 volt. Okay,
Okay.
and other things are transition periods and turn on and turn off. So when we calculate this pin conduction, we see set into ID into D.
Into D.
Whether D is having considered turn on and turn off time or not.
Okay. Let me see the problem. Yeah, this is the problem here.
Uh,
On time is given,
on
operating
time
frequency is given. So
50 microsecond. So is the on time, it is total on time considering T on and T off also.
T on is just this 50 microsecond is conduction period, and
Okay,
all time is this where it is
10
getting turned.
microsecond.
Yes. And the right time is this one, 5
Okay.
microsecond,
Uh,
and total time is your 10 kilohertz. 1 by 10 kilohertz will be
100 microsecond.
100 microsecond. Yeah.
So 100 microsecond here D means zero point 0.5.
D means 0.5. Yeah, that
D
would be
is
the.
0.5. Okay. We have excluded T or turn on and turn off time. It is not included in the. Okay. And then switching loss, while considering switching loss, that the watt loss across the switches when it is turned on, we have to calculate that and we have to average it out for the total period, isn't it? We have to sum this loss plus this loss, first loss and second loss, and
Yes.
make it average for the whole cycle.
See, there are two ways. You can prefer any way. First thing is you compute energy during turn on and turn off, right?
Energy. Okay.
energy and you multiply it with switching frequency directly. In turn on and turn off, both will give you switching energy loss. And if you
Okay.
multiply it with 10 kilohertz, that will be your switching loss. Other way, you find out the energy lost during turn on, right, for this period, and individually you multiply either with turn on and turn off. So any way you can go, right? Did you get
Okay, we'll calculate and come to know.
because once it is rising and once it is falling, so it is happening out of one time period only. So
Okay.
either individually you can compute or you can add up both and you multiply it with six.
Switching frequency.
Yes.
Okay. We have to add for the cycle both the
Uh,
losses and multiplied with the switching frequency.
yes, yes. Okay.
Hello.
Yes.
Just I have one more doubt here. Question number 8. It is asking us to refer question number 2 for the other data, right?
Okay.
So if we go to question number 2, we have a basic information related to VB. If you can see here, the beta value is given, and RB resistance means base resistance, and also the VB value is given. From this data, I think we can calculate the value of collector current, right? But my doubt is like, how do we calculate saturation value with this available data?
VC is that if you are not able to compute, you can directly take the standard value that is zero point 0.2 volt if you are not
Okay,
getting any way to compute. If there is a way, you need to go through that. But generally, VC is at is zero point 0.2 you can consider. Just like that, you take uh, forward voltage at zero point 0.7 or zero point 0.6 volt in silicon devices.
okay. And also, we need the duty ratio for this calculation of conduction loss, right? So here, the turn on time, all those information is also not available.
In question number 9, you are asking.
No, no, in question number 8.
In
So they're
question
asking
number,
us to calculate the conduction losses.
okay. So in previous problem, if duty cycle is not given or duty ratio is not given, you can consider that it is conducting for a whole time period. Just if it is not given in that case only. If it is mentioned, if it has
I
mentioned that it is getting switched and all those things are happening, since I
think
haven't
that's
gone
a
through this problem,
DC.
sorry.
Yeah, I think that's a DC supply. 15 voltage DC it is mentioned.
Okay, so if it is a DC thing and no switching is there, let me go through the problem once. I haven't seen this problem before. This emitter is grounded. Yeah, so as DPS I think correctly pointed out, it is a DC, so you can find out conduction losses as considering D is equal to 1.
Yeah.
Okay, good. Thank you.
Okay.
And I think this same question was asked in the ask a question in the session, and I think it was replied like if there is incomplete data, you
Yeah.
should question may be deleted. I don't know whether.
No, no. Actually, in that problem also there was DC supply only. If you
I mean, just now when I was asking that the missing point is RC is not there in this problem. So
in
to calculate the VCE,
uh-huh.
uh, we should have RC also to be given in the question number 2, but it was not given. So you have mentioned that we can consider VCE as a zero point 0.2 volt, right?
Yes,
If
yes.
it is not given. Yeah, but what I'm saying is in the question answers, I mean, we are having a question answer session uh, in the
In
Swayam
that
itself. Yeah,
uh
in the Google Sum, there somebody was asking the same question and it was answered like if the question is incomplete, you should consider it as it will be deleted. I don't know. Yeah. So maybe we can. I think better maybe as you said we can solve this problem with value 2.2,
yeah,
and if it is getting deleted, let it get deleted.
yeah, it will be for everyone. Like
Yeah, yeah, yeah.
But over there, IC is there, na? you can calculate that RC.
IC is there, but VC is not there. Basically,
For 8, you can consider 15 for VCC.
VCC is there.
Hmm.
Basically, the equation that connects is VCC equal to ICRC plus VCE, right? So here two things are not there, like RC is not there and VCE is not there.
VC is there, na? 0.2.
VC is not given in this equation. I mean, in this question.
Sir is telling that it is, you
Yeah,
can
yeah,
take.
yeah. That's clear. I mean, now it's yeah, understood. If it is not given, we can consider it as
Yeah,
0.2.
you
That's
can
clear.
put it.
Yeah, understood. So is there any relation that we can have between the reverse recovery chart? I'm talking about power diodes.
Mhm.
So
Yeah,
QRR, TRR, and DI by DT something.
yeah. That relation professor has explained, I guess. Okay, so I will go through that concept really quick.
Like,
Uh, See, so that diode reverse recovery thing we approximated with a triangular, right? And whatever the charge was
yes.
stored that get discharged during that period, and it is two period TA and TB we considered, and total time was considered as reverse recovery time,
Yeah.
TRR. Yeah. And this is nothing but IRM, peak reverse current, that you can get from dataset. IRM you can get from dataset. TRR, TA, and TB you can get it from dataset. There is a relation uh, since this is a triangular waveform. You can compute QR equal to half into IRM to TRR. This is the expression professor also derived.
Yes.
Right? So
Yeah.
where you have particular doubt, can you point
Yeah. Is there any relation between QR,
QR
TRR, and DI by DT? Like
DI by dt?
change
Okay.
of yeah.
So if you know IRM and this is the 0 point, so DI by dt is nothing but IRM by TA.
Yeah. Yeah.
Okay? And IRM you can compute from this first formula,
Mm,
and this is the second form. And
yeah.
if you want to derive another formula or another equation,
Got it.
you can get TA plus TB. So you have three equations. You can plug in any values.
Yeah. Sure. Understood.
I think this is doubt regarding last problem of assignment.
Thank you on that. Yeah.
Thank you. Yeah. Yeah. So I was about to discuss that VC stat problem.
Hello,
Yeah.
sir. Can you send the recorded session link in the chat?
In chat box, I think I have shared the link of YouTube channel where I will upload this session. Did you not get that link?
Oh, actually, I missed it.
Okay. Okay. I will share it
Huh.
once more. In the end,
Huh.
you just say at the end of the session I will share one.
Okay, sir. Okay.
So I was trying to explain that uh, why do we operate transistor as a switch in saturation region? But we will come back again to the problem which was asked. So circuit was something like that. Let me bring back the circuit. So this is circuit and this is a PNP transistor. So here all the terminology will be interchanged. So this will be emitter, this will be collector. So this is still base. Okay. So in this question, we need to find out in which operating region this transistor is working. Okay. So see, in this problem also it is written explicitly that take VC sat is equal to zero point 0.2 volt if necessary, right? So it means that if this transistor is operating as a switch in saturation region, then you can take VC as zero point 0.2. Otherwise, you will have to go ahead with linear circuit. Okay. So let me see. So uh, we are moving ahead with consideration of this circuit as a switch or it is operating in saturation. Just like basic analog problem where we first consider it is working in linear, and if it is wrong then we will verify whether it is working in saturation. So in that manner we are starting with assumption of saturation, right? This is assumption. If this is assumption, we can safely take VEC is equal to zero point 0.2. So if VEC is equal to zero point 0.2, we can compute IC. And when will I get to know that this switch is working in saturation? When IC is less than beta IB. Okay. Then we can say that this switch is working in saturation mode, or this device is working as a switch. So, sorry, this is IE. This will be. So, if we are considering it is working as in saturation mode, VC sat, we can take it as zero point 0.2 and we can compute IE is equal to 10.7 minus zero point 0.2 divided by 5 kilo ohm. So that will lead to the value of 2 milliamperes. Sorry, I think I did some mistake. Uh, See, it is
5
a
volt.
sorry, it is a PNP transistor, so it is easy to get confused. So here, this is VE and VB. So VBE we have to consider here. VBE equal to zero point 0.7 volts. So that's how we will compute. So 10.7 minus VBE divided by RE, not RC, since this is an emitter terminal. So it will lead to 2 milliampere. This is IE here. Now, beta is given here 100, but we cannot directly take the relation of IC and IE in terms of beta since we have assumed that it is working in saturation region. So, what we need to do, we can compute individual voltage VE and VC, right? VE and VC, we know the relation VE minus VC will be zero point 0.2. So, this is first condition we have obtained. Second is VE minus VC is equal to zero point 0.2. And the third condition we can compute in terms of VC and this IC RC plus this terminal. So another equation we can write this VC is equal to IC into 5.5 kilo ohm minus 5. Okay, so we are left with the computation of IC, and IC will be IC will be VE. Just give me a moment. V minus VC is 0.2 volt. VC is equal to IC into 5.5 kilo ohm minus 5. And before that, VE we can compute. VE, since IE we have computed. So if we compute this voltage VE, if we compute this voltage VE, we know the difference between VE and VC. And then we will get to know the value of VC. And after that, we will able to compute IC from the difference between VC and this potential. So and that's what we are trying to do here. So IE we computed 2 milliampere, so VE will be equal to 10.7 minus 2 into 5 kilo ohm. So that will be 0.7 volt, I guess. Yeah. So VE will be 0.7 volt. And we know the VCE sat is equal to 0.2 volt. So VC will be point, sorry, VE minus VC is equal to 0.2. So VC will be 0.5 volt. Okay. So we computed VE and we computed VC. Now we can compute this IC current since we know the potential at this node. So IC will be 0.5 minus 5. So that will be plus 5 divided by 5.5 kilo ohm. So that will be 1 milliampere. So IC we computed 1 milliampere. Okay. And now we computed IC, we have IE. Now we can easily compute IB and we will verify IB equal to IC equal to beta IB or not. So IB, we will apply KCL at this node of transistor. So IE plus IE minus IB equal to IC. IE minus IB equal to IC. So this is the KCL equation at this terminal. I is entering the node, IB will leave the node, and IC will again leave the node. So I minus IB equal to IC. So IB we can write it as IE minus IC. IE by 2 milliampere, IC was 1 milliampere. Overall IB is equal to 1 milliampere. And we can see IB is 1 milliampere and beta is given 100 in this problem. So IB, IC should be less than beta IB. So that will be 100. IC should be less than 100 from the condition of saturation. Condition of operation in saturation region. So from this condition, if it is satisfying, and we can see that IC is 1 milliampere only, it is way less than 100 milliampere. So of course it is operating in saturation region, and we can say that this switch is working in this saturation region, and this transistor is working as a switch. So we had four options: whether this BJT is operating in cutoff, saturation, reverse active, or active region. So we had to check one option, and we can see that it is operating in saturation region. So I hope this is clear. Any doubt in this problem? We move.
Sir,
Yeah, course.
uh, same one question regarding that question 9 of the assignment of BJT.
Okay.
That P loss is considered P conduction plus P switching plus P off period loss.
Yes.
We have to take 3 losses, isn't it?
Yeah, three losses, or you can say four losses. Switching off, switching on losses, if you consider it as a
Okay, that is a single switching loss.
okay, yeah, then three losses. Yeah.
3 losses. Okay. And one another question about that first question of that assignment, that if the capacitive loading of the BJT, the only it will affect the T off, T on, or both.
Actually, I cannot directly answer this problem.
But
Sorry
you
for
can
that.
give the just hint of that for me.
Uh, in in first or second lecture, professor did this kind of thing where he connected the load, simple resistive load, and he mentioned at that point, if the load will change, that these things will change.
First 2 lectures
First two lectures of
of BJT.
BJT.
Okay.
In either in first or second, he mentioned particularly that I am considering resistive load, but if you change it with inductive or capacitive load, you will see the difference in that parameter. So I think it is mentioned there. More than it, I cannot reveal. So
Okay. Thank you.
thank you. So I hope this is all. Time is also up. So I will share that link again once more. Uh, so thank you everyone for attending. I hope
Share the link, sir, please.
I have shared in chat box just now the YouTube channel link where I will upload within 15 minutes.
Chat box, is it open?
Yeah, it is open.
YouTube.com. That okay, okay, okay.
So is the three sessions, right? I mean, three sample problem. Is it kind of repeating, or is it okay
Yeah,
to attend any one of them? I mean, so
uh,
that is the same topics are discussed, anything like
yeah,
that.
same topics are discussed by three different person. So
Okay.
basically, it is independent kind of thing. So
Mm.
no relation between all three.
Okay. So basically, it's covering these sessions which I mean, professor has taken, right?
Yes, yes.
Okay. Thanks a lot. Thanks a lot for your session.
Thank you.
JDS@IITB.
Yeah, yeah, that's the channel name.
Okay, okay.
Okay, then any final doubt? I am here to take for 1 or 2 minutes. So then we are done with today's session. Yeah, I will be taking every Tuesday session.
Okay, thank you, sir.
Thank you. Thanks a lot. Thank you everyone for joining. We will
Thank
meet
you.
again next Tuesday.
Bye.
Bye.
Bye.